when a forward reaction and a reverse reaction are occurring in a dynamic state, where we're looking at a forward and a reverse reaction being written with double arrows. The concept of equilibrium will be the topic of our next 3 chapters. You can see just by the devoted time, I'll get that out, the devoted time to the concept of equilibrium, we can see that it's quite a large and important concept. So we'll begin by looking at some very basic ideas first, and then taking a look at how we apply those in a mathematical situation. Reactions are reversible. Let's just make up a forward reaction where reactant A and reactant B go forward and to create 2 products we'll just call C and D, just some generic chemistry. And looking at the reverse reaction, we can see that C and D go back indeed to form the original A's and B's. So a forward and a reverse reaction are occurring. Notice initially, and we would call that as time 0, we only have a forward reaction occurring simply because we have no product made at time 0. As time goes by, C and D begin to accumulate, and we can see that a reverse reaction begins to form, and it all goes back to what we called the collision theory. We must have molecules collide for bonds to break and new bonds to form. And if reactant A and B are the only things available to collide, well, we're only going to go in one direction. But as C and D begin to accumulate, the chances of their successful collisions also guarantees a reverse reaction. And eventually, the rates become equal. The forward and the reverse reaction reach an equilibrium state where you can see it's the flat line on our graph. I want you to jot this graph down in the little margin area. You're hearing my dog Sadie bark. Sadie. We have a XY axis as time is going by on the x-axis. We have the rate of reaction. That goes back to what our kinetics chapter talked about. In kinetics, a forward and reverse reaction over time develop an equilibrium. You can see, and I want you to label the forward reaction. The rate at the beginning there is quite fast in comparison to the reverse reaction. Of course, that starts at a 0, 0. There is no reverse reaction at time 0, but given enough time to accumulate more and more product, we start to see the reverse reaction take off. Notice that an eventual flat line is achieved, and that indeed is the state of equilibrium. So what is equal at equilibrium? Well, the rates are equal. Kinetics, how fast the reactions are occurring. But, very important, it does not mean that concentrations are equal. I'm saying that reactant A and B compared to product C and D don't have to have the same amount present. We might be creating far more product, or we might be creating far more reactant in comparison to one side of the arrow or another. The forward and the reverse reaction are occurring at the same rate, but not necessarily guaranteeing me the same amount of reactant and product. Rates are determined by a lot of different things. Concentrations, activation energy, the temperature, all kinds of things as we studied in our last chapter on kinetics. So that net concentrations do not change at equilibrium. It's a very powerful statement. Once equilibrium is achieved, the concentrations of reactants and products remain unchanged. That was the flat line if you glance back at your graph. So as time goes by, we achieve the same rate of forward and reverse reaction, where we reach an equilibrium state of the amount of product and reactants. This concept of equilibrium, let's just begin by thinking about that in terms of a big equal sign. Those double arrows, I have a hard time typing those in PowerPoint. A forward and reverse reaction typically are seen as a double arrow, one on top of the other going into the right and one heading to the left. Sometimes I'll just type a simple equal sign just because it's easier to type than to try to create a forward and a reverse arrow. But if we look at an equilibrium for dinitrogen tetraoxide, and it's in a gaseous form. I have a forward arrow and a reverse arrow. That's the best I can do for an equilibrium sign. And it goes on to form 2 molecules of nitrogen dioxide, so NO2. It's a balanced equation. Remembering kinetics, we assume that these are both elementary reactions. Now I'm going to take us back and stress what I've just said. In the very last section of our kinetics chapter, we talked about reaction mechanisms. And whenever we wrote a dynamic equilibrium with the forward and reverse reaction, one going forward, one going in reverse, those were always elementary reactions. They were a part of a multi-step mechanism. Every one of the equations we're studying in a concept called equilibrium are indeed elementary reactions. They may be part of an overall reaction mechanism, but each elementary reaction will be studied in terms of equilibrium. Consider that in terms of its kinetics. We get our rate laws directly from the elementary reactions. So when I'm looking at N2O4 in equilibrium with 2 units of NO2, I now know that there's a forward reaction with a K forward and a reverse reaction with a KR, we'll call it for reverse, where we can write a rate law from their equation. Now remember from last chapter, rate is equal to K times the concentration of the reactant raised to some power. If I think about what F is standing for by that K constant, it's standing for the forward reaction. Just automatic pilot from our kinetics chapter. If I'm looking at the forward reaction, the reactant is N2O4. Its coefficient is a 1. Write a rate law for that elementary reaction. We'd write that rate, and that little f is just showing you I'm referring to the forward reaction. Rate is equal to K times the concentration. Remember the brackets are molarity units. Concentration of molarity. So the bracket there, I would read that. Rate is equal to K times the concentration of N2O4 with respect to first order. Read the reverse reaction and jot down its elementary rate law. The rate of the reverse reaction is equal to its K constant times NO2 to the second order. That concentration of NO2 would be the second order based on the stoichiometry. Notice it has a coefficient of 2. And if it's an elementary equation, the rate law comes directly from the equation. At equilibrium, thus the term equilibrium, the rates are indeed equal. If the rates are equal, we can set up our rate law for the forward reaction directly equal to the rate law for the reverse reaction. Kf times the concentration of N2O4 to the first power, set equal to Kr times the concentration of NO2 to the second order. The forward and the reverse reactions are indeed at equal rates. What I'm going to do now is rearrange this ratio to get the K constants by themselves. So what I'm hoping to do, if I think about what we just had, Kf set equal to Kr, I want to get the K's on one side and the concentrations on the other side. So we'll do that by simply dividing both sides by Kr, the reverse, divide both sides by Kr, so you simplify, and then divide both sides by N2O4. We get the following expression. The concentration of our NO2, which is our product, raised to the second power, set over the concentration of N2O4 to the first power, is equal to this ratio of the forward rate constant over the reverse rate constant. This is the very definition of an equilibrium constant. We're going to just simplify to K, Kf over Kr. If the rate law constant for the forward reaction is the rate law constant over the reverse reaction, Kf over Kr defines the term equilibrium constant. It's a ratio that compares the K constant of the forward to the K constant of the reverse. And look how it's calculated. Product over reactant, where coefficients come directly to the power with which it's raised because these are elementary equations. Products over reactants, stoichiometry dependent. Notice it says once equilibrium's reached, the concentrations of those reactants and products no longer change. We mentioned that on the previous slide. There's no net change. This is a flat line of the graph that we just drew together in the margin. This reaction is now in a state of dynamic equilibrium. Dynamic equilibrium. It's the opposite of static equilibrium. Dynamic equilibrium. Things are moving. They're just moving at the same rate. Let's put that into a more general form, known as the law of mass action. We'll make up a general equation, reactant A with its coefficient of small letter a, plus reactant B with its coefficient of small letter b, is in dynamic equilibrium. Notice the double arrows. Did a little better job there for us. A double arrow, best I could. Creating products C and D with their respective coefficients represented by small letters. When I think about writing out an equilibrium constant, Kc is going to stand for an equilibrium constant that's using molarity for concentration units. The product, C times D, raised to the power of their coefficients, set over the reactants, A and B, raised to the power of their coefficients. Products over reactants, where the coefficients become the order with which they're raised. And I'll stress once more that's fair to do because these are elementary equations. Last chapter, when we were writing rate laws, we had to use initial rate data to determine with which respect these powers were raised, because these were looking at general equations, not guaranteeing you that they were elementary. Dynamic equilibrium, forward and reverse, are always are always elementary reactions, so therefore the stoichiometry becomes the with which the power we raise their concentrations. Brackets stand for big M, molar units. Products over reactants, coefficients become the power with which we raise them, and we get this expression called the equilibrium expression. So we call this relationship of products over reactants the equilibrium constant expression. Products over reactants. If I say it enough, hopefully it sticks. Kc is a number. That's it. There's no units to it. It's a number. Kc is a numerical value obtained when we substitute the equilibrium concentrations into the equilibrium constant expression. Plunking in numbers for the values, products over reactants, gets us a number, and that number is called the equilibrium constant. The subscript C does not stand for constant. It stands for molarity units. We'll notice here in a moment we have a Kc for concentration equilibrium, and we'll have a Kp for pressure equilibrium. Kc and Kp are the only two different types of equilibriums that this course will study. Kc is the equilibrium constant using molarity units, C standing for the concentration values in molar units. So the subscript is telling us big M molarity units. We know that it's stoichiometry dependent because these are elementary reactions. So they're part of a larger mechanism. Kc at any given temperature does not depend upon the initial amounts of reactants and products. We see that when we drew that graph, we had a high amount of reactants, they got used up. Products begin to form, and somewhere they'll meet and flatline on our graph. The value of Kc really only depends upon the particular reaction and the temperature with which you're running it. Of course, we know that raising temperature changes K constants from the Arrhenius equation in our last kinetics chapter. Let's just simply practice writing expressions. No numbers in terms of concentration values, but we just want to practice what does the expression look like. We're being asked to write the equilibrium expression for Kc for the following elementary reactions. The first example reads 2 O3s is in equilibrium with 3 O2s. Ozone is O3, molecular oxygen is O2. 2 moles of ozone rearrange to form 3 moles of oxygen. We're being asked to put that into Kc equilibrium expression, where the concentration of molecular oxygen cubed set over the molarity concentration of ozone squared. What might that look like? Take down a guess. We have 2 units of NO with 1 unit of chlorine in dynamic equilibrium with 2 units of NOCl. Think products over reactants. The stoichiometry determines with power with which we raise the orders. Brackets stand for molar units. Take down a guess. How'd you do? In our first example, Kc, I'm using brackets because it asked me to represent the concentration equilibrium. Kc stands for brackets. Those represent molar units. Capital M for molarity. We said the molarity of oxygen, molecular oxygen, O2, cubed, set over ozone squared. Products over reactants. Stoichiometry becomes the power with which we raise. In your second example, products over reactants, we see the following. The product, NOCl2 squared. Inside of a bracket, NOCl2, because we're using that to represent the molarity of our solution, capital M. Set over the product. Now, product, I just used that. That might have been confusing. Product, I meant that as we're multiplying. When you multiply, you get what's called a product. But I probably should use a better word because on the bottom goes reactants. Products over reactants. And when I said the word product, I meant to multiply the bottom. So hopefully that didn't confuse us too bad. NOCl2 squared set over NO squared Cl raised to the first power. I'm multiplying those two values on the bottom. Products over reactants, stoichiometry dependent. So writing the expression is quite easy. They come from the elementary reactions and just kind of put them in, products over reactants. And here's a nice idea. I know that in our last chapter, the rate law, constant K, we had to work out a little formula to help us derive the units. We said it was 1 minus the overall order per second or per minute, whatever the time was. But now, since we're using a ratio for the equilibrium constant, products over reactants, where equilibrium constant truly is being defined as a ratio of Kf over Kr, forward over reverse, those ratios actually just cancel out. It says, technically, these do have thermodynamic measurements, measured in activities, not necessarily M, concentration units, or atmospheres of pressure. And it's beyond the scope of this course. It's beyond the scope of any master's level course I've ever had. It's just common practice to say there are no units on an equilibrium constant. There are no units on an equilibrium constant. Now, let me clarify. Yes, there's a unit on a rate law constant, kinetics chapter. There is no unit on an equilibrium constant, equilibrium chapter. This is a ratio of forward over reverse. We'll commonly just simplify to say no units. So no units is a good thing. If that's a question I ask you in class, is there a unit on that? You simply say no. K is indeed a constant. It's constant at any temperature. We said temperature affects the rate, but once a dynamic equilibrium is established, it indeed holds constant. So equilibrium simply sets a position for the concentrations. K is a constant. Temperature affects the kinetics, but not the K in equilibrium. I'd like you to prove that to yourself in the following way. First of all, here's our equation for some experimental data. We have 2 units of NO2 forming from 1 unit of N2O4. The reactant here, N2O4, and the product, 2 units of NO2. We ran 4 different trials, varying the initial amounts of the reactant and product. In the first trial, we started with 0 N2O4 and O2 molar of product. Notice there's an equilibrium. Equilibrium constants must be calculated from equilibrium concentrations, not from initial values, but from equilibrium values. The expression, jot this on your paper. What would the expression look like for this reaction? Product over reactant, stoichiometry dependent. We'd see Kc set equal to the value NO2 squared, set over N2O4, product over reactant, squaring the product, coefficient of 1 on the reactant. I want you to take a moment with your calculator and solve for Kc for each of these 4 trials. The value of NO2 squared at equilibrium, set over the value of N2O4 to the first power at equilibrium. Even though we have varied the initial amounts, what we're starting with, I want you to notice when equilibrium arrives, what happened to the K constant. Pause the video, calculate Kc for every trial, and in your margin note, I want you to write down for me not only the values of Kc for every trial, filling in that blank, write down your observation. How did the initial data affect the equilibrium constant, Kc? Pause the video and start up when ready. I bet you've noticed every trial that you calculated. Trial 1, 0.2113. Trial 2, 0.211. Trial 3, 0.213. Trial 4, again, 0.213. You calculated 4 different trials and came up with the same K constant. K is indeed a constant. Your observation, the initial amounts of reactants and products did not change the equilibrium constant. That the ratios that were established at equilibrium always give me the same constant. Now, emphasis on what I'm trying to say, easy. Never use initial amounts, always use equilibrium amounts when calculating for K values. We've mentioned KCs, standing for concentration molarity units, and I made note, kind of seeding this, that there is another type of K constant for pressures, and that will get a Kp. When the reactants and products are all gases, we can formulate the equilibrium constant expression in terms of partial pressures instead of molar concentrations. Instead of using brackets, which stand for molar units, we use a capital P for pressure and then sub the reactants and products, subscript the reactants and products. If our equation showed A plus B forming D plus E, I don't know why I did that. A plus B makes D plus E. Products over reactants, but using partial pressure denotion. This is what I would read. Kp is equal to the partial pressure of product D raised to the coefficient D times the partial pressure of product E raised to its coefficient E, set over the partial pressure of reactant A raised to its coefficient A, and the partial pressure of reactant B raised to its coefficient B. The only difference is instead of using brackets, we use a capital P to denote pressure. And in this chapter, as with all equilibrium expressions, we'll always use atmospheres for our pressure unit, ATMs. Standard pressure in an atmosphere is 1. Sometimes if you're given torr, millimeter of mercury, you may find it just convenient to flip that to an atmosphere so that when we calculate from Kc to Kp, we come up with a common answer. Products over reactants, stoichiometry dependent. If we use molarity units, we get something called Kc, and if we use pressure units, we get something called a Kp. So concentrations, Kc, pressures, Kp. For any given reaction, the values, an actual number, the numerical value of Kc is going to be different from the numerical value of Kp's. Remember, pressures only come from gases. Molarity units can either be gases or aqueous ions. So we want to indicate, let the reader know, are you referring to a K that's a concentration or a P for a pressure? We have to be able to look at what kind of K. So notice the denotation in this title, Kp, now I know you mean pressure. Kc, now I know you mean concentrations. So every good K constant should have a P or a C. Although I'll tell you, sometimes I see KEQ, K little subscript EQ to just denote an equilibrium constant, and it's just put in there to use it for a mathematical problem. Wouldn't matter if it's KC or KP. So sometimes in various texts I've seen KEQ to just let you know it's an equilibrium constant. Ideally, you would let the reader know if that equilibrium constant was being measured with molar units or with atmospheres of pressure. So KEQ, I'm just sharing, I've seen that out there. I think even some of our multiple choice questions will use that general KEQ formula. Well, how are molarity and pressure actually related? And of course that all ties back to that ever popular Pov-Nert equation. That equilibrium measured in molar units and equilibrium measured in pressure units can easily be converted from one into the other form. Kc's into Kp's and vice versa, all tying back to Pov equals Nert. So let's jot down, if PV equals nRT, we know pressure, atmospheres, volume must be in a liter, N stands for moles, R is the gas constant, 0.0821 for the atmospheres of pressure, and Kelvin temperature. Knowing that moles per liter is the very definition of molarity, I'm just going to rewrite Pov equals Nert, showing in this parenthesis N over V. Moles over volume, moles over liter. Really, that's just saying P equals MERT. That sounds familiar from our colligative properties, doesn't it? And knowing that if moles per liter gives us our a bracket, and that's molar units, the pressure for substance A is now written with a bracket RT. The bracket means molar units. The concentration of this substance A in molarity units times R times T. R is 0.0821 and T is the Kelvin temperature. So we just rearranged a little Pov-Nert. And now, looking at that, we have derived the following formula. Write this down big, carefully, circle it, box it, somehow show yourself. When I'm being asked to convert from a Kp to a Kc, or a Kc into a Kp, it's a plug and chug formula using the following. I initially just showed you how I derived it. Kp can be found by taking the Kc, multiplying RT, and raising that R times T product to the delta N. What does that mean? The delta N. Well, delta we know stands for change, and N is the number of moles. Delta N is the change in the number of gaseous moles in the chemical equation, comparing products to reactants. Delta N is simply taking the moles of just gases, emphasize that to yourself, just gaseous product moles from gaseous reactants. Products minus reactant gaseous moles. So it's just a subtraction from the coefficients of those things that are gases. Kc times RT raised to the delta N. Quite easy to use. Delta N, moles of gaseous product minus gaseous reactant. Let's show you one. Let's try one. And I think you flip your page to actually see the problem here. I'll read it for us. It says, in the synthesis of ammonia from its constituent elements, Kc is given as a value of 9.6. Notice no units, just a number, 9.6. And it was recorded at 300 degrees Celsius. If we know the Kc, I'm being asked to calculate the Kp for this reaction at this particular temperature. Well, step one. Let me see on your paper the balanced equation for making ammonia from its elements. Step one, as any good chemist does, they write out their recipe. Gaseous nitrogen reacts with 3 moles of gaseous hydrogen. There's the best thing I can do, a dynamic equilibrium arrow, to form 2 moles of gaseous ammonia. N2 plus 3H2 forms 2NH3. All reactants and products are gases. Now remember, Kc was what was given to us. Kc was given in the problem as 9.60. Alrighty. So we're being asked to change Kc into Kp. Remember our formula. You boxed it, highlighted it, scored it somehow. Kc times RT raised to the delta N. Now let's figure out what delta N is while we're staring at this equation. How many moles of gaseous product do you see? I see two in front of the ammonia. How many moles of gaseous reactant do you see? Well, I have 1 from the nitrogen plus 3 more from hydrogen. I'm seeing a total of 4 gaseous moles on the left side of our arrow. Remember, the delta N is products minus reactants for gases only. And I'm looking at a value of 2 minus 4. We get a -2. So the delta N, -2. Plug it in. We were being asked to solve, just convert a Kc into a Kp, plug and chug. The original value of Kc given was 9.6 times R times T. Now where did the 573 come from? Well, remember the story problem gave us 300 Celsius. I added 273 to turn the Celsius into Kelvin. Now hit it on your calculator. It's the product of R times T raised to the -2. RT in a parenthesis raised to the power of -2, and then multiply by your 9.6. Remember, there's no units on equilibrium, but what'd you get? Write it down on your paper. When you record your answer for Kp, I found 0.004338. Probably didn't record as many decimals. I got carried away. No units, just a number. It's a very small number. It's giving me an indication that most likely the reactants are being favored in this equilibrium. And we'll talk more about the number itself. The magnitude of the number is what's interesting to a chemist, not so much what it is, but the size it comes out to be. Let's try another. I'll read it with you. For the equilibrium of sulfur trioxide decomposing into sulfur dioxide and oxygen, the Kc is 4.08 times 10 to the -3rd power at 1000 Kelvin units. What's the Kp? Begin by writing out your balanced chemical equation. Turn these words into a balanced equation, jotting down the value for Kc. I hope you pause when needed. Don't cheat yourself from the practice. Pausing and stopping is always a good practice with the video lessons. But I bet we match. I bet you wrote down 2 moles of sulfur trioxide in the gaseous form in dynamic equilibrium with 2 moles of sulfur dioxide and a mole of oxygen. And I re-put in our, is that a word? I put back in our equation how to convert from Kc into Kp, knowing we take the original Kc from our story problem, take the product of R times T and raise that to the delta N. Delta N is products minus reactants for gaseous moles. Kp that was given, or excuse me, the Kc from the story problem, Kp is what we're calculating for. 4.08 times 10 to the -3rd power. The R constant to match atmospheres. August 21st is how I remember this number for whatever reason, 0821. The Kelvin temperature is 1000. R times T raised to the 3 minus 2, that's product gas minus reactant gas. I see 3 minus 2, so raised to the 1st power. Hit that. Pause the video, hit it, and see what you get. I'd like to know that I don't have a calculator mistake. See if you get the same answer. How about something close to 0.335? Kc converted to Kp. We're now ready to begin looking at the equilibrium constants, trying to get a little piece of information about what it is it's telling us. It's the size of the number that a chemist finds interesting, not necessarily what the number is, but how large or how small it is. That gives us an indication of what's being favored in this equilibrium. The forward reaction toward products, or is it the reverse reaction toward the initial reactants? So the magnitude of the equilibrium constant, they range from being very, very large to very, very tiny numbers. Looking at the number itself, the K constant, if we find it very large, much greater than 1, what we're saying that is that equilibrium lies to the right. Forward reaction is being favored. We call that products. The product side is being favored. Think about what we've just said. If the equilibrium constant is products over reactants, and I have a large amount of product, I'm going to get a big number when I solve for the ratio. And the opposite is true as well. If K is quite small, the equilibrium lies to the left and the reactants are being favored. We'd say the shift is to the left, favoring the reactant side. Product over reactants, and if that reactant there in the bottom of our ratio is the large number, the equilibrium constant comes out quite small. So the magnitude of the number is what's interesting. And let's reinforce that, and this is what I'm going to call a margin note. And write this down in the margin of your notepad page. We'll write an equation, N2 plus O2 in dynamic equilibrium with two NOs. Record the Kc, and this is molarity for concentration. Kc is 1 times 10 to the negative 30th. 1 times 10 to the negative 30th. That's a whole lot of decimals in front of the number 1. What does that number mean? Well, that number is very small. The Kc is so small that the amount of product being made is negligible compared to the amount of reactants. Looking at the sheer size of this K value, very small, the equilibrium lies to the left. The reverse reaction is being favored. Sometimes you'll see me emphasize that, as I've done before, where I'll do a dinky arrow pointing to the right and a large arrow pointing to the left, indicating that reactants are being favored. So the size of the number, the magnitude, how big or how small it is of interest to the chemist. It gives us an indication. Now remember, the rates are equal, but we don't necessarily have equal concentrations. The only time that happens if K comes out exactly 1. If K is exactly 1, we have the same amount of product as we do reactant. The same number set over itself gives me a ratio of a 1. So the first part of the lesson here in this section, interpreting and working with equilibrium constants, the discussion simply talked about how large or how small the K constant is, giving us an indication if products are favored or reactants are favored. The next part of the lesson in this section really are applications of Hess's law. Now, Hess's law, originally from our thermodynamic chapter, talked about delta H, the enthalpy of reaction. Enthalpy, heat of reaction, I like that word also, exo and endothermic. Well, we're not caring about heat in this particular chapter. We're caring about the equilibrium constants, and yet really a lot of the same Hess's law rules apply when we're looking at adding equations together to find Kc's. So I'm looking at a Hess's law application, but not in terms of heat energy, in terms of K constants, either Kc's or Kp's. So the next series of slides are looking at applications to Hess's law. For instance, the direction of a chemical equation and the K constant, the equilibrium constant. If we had an original equation where A plus B goes to C plus D, just some general equation, what would the reverse reaction look like? Flip the direction. Well, we'd have reactants now, C and D, making products of A and B. If we reverse the reaction, it has a new equilibrium constant because the constant is product over reactant. What's on the right side set over what's on the left side. You flip the direction, we really are changing the K constant. So it says this new equilibrium constant is now going to be called Kc prime. The product over reactants is now the reciprocal of the original K constant. If you flip the direction, you take the reciprocal of the original K constant. We don't necessarily do this as positive and negative, as Hess's law would indicate for endo and exothermic. Now let me repeat that. Originally in Hess's law, when we use heats, delta H equal, we wrote positive for endothermic and negative for exothermic. This is very different. We're not using heats here, we're using equilibrium constants. But the idea of flipping the direction of the sign really is an application of Hess's law. If I flip the direction of an elementary equation, the K constant doesn't flip. What it does is you take the reciprocal. Products over reactants have simply flipped direction. So when I reverse a reaction, or flip the direction, if that's easier, it's the reciprocal of the original K. Write this down. In your margin, write this down. The value of Kc prime and Kc are reciprocals of each other. Kc prime is the reverse reaction. When you reverse a reaction, you take the reciprocal of the original Kc. Write that down. See, let's put that into practice. Let's write the equation for the formation of ammonia from its constituent elements. Kp is provided as 4.34 times 10 to the negative third power at 300 Celsius degrees. What would Kp for the reverse reaction? Well, step one, as any good chemist does, we write a balanced equation. On your paper, write with me the forward reaction, and we'll put at the end of that chemical sentence the value for Kp. The constituent elements of ammonia are molecular nitrogen and molecular hydrogen, and we see the stoichiometric ratio of 1 to 3 to 2. The Kp for this equation, the forward direction, provided for us is 4.34 times 10 to the negative third. No units on an equilibrium constant. Let's now write the reverse reaction, where molecular ammonia forms its elements, molecular nitrogen and molecular hydrogen, and that stoichiometric ratio of 2 to 1 to 3. Reverse the direction. Kp prime, all that little hyphen there, or apostrophe, whatever it looks like, Kp prime is why we read that. It's the reciprocal of the original value. When you reverse the reaction, 1 divided by Kp, and I found that, but please double check my calculator skills, 230.41. When you reverse the direction, you reciprocal the original value. Now what does that magnitude of K indicate? Write this with me as well. Write it in the same area. We already have on our paper the forward Kp value, 4.34 times 10 to the negative third. What does that number mean in terms of its magnitude, the size of the number? I think that size of the number is quite small. It's a small number, 0.00434. Very small number indicates the left side of this reaction is being favored. What's on the left side? Well, that's nitrogen and hydrogen. Look at the magnitude of the K constant from the reverse reaction, 230. Now that to me is a big number. The big number indicates the product side is being favored. But what's on the product side? Oh, it's nitrogen and hydrogen. In the forward direction, the small number indicates N's and H's are favored. And even if you flip the direction, the magnitude of the sign also changes to stay indicating the nitrogen and hydrogen. So simply reversing the direction still indicates which side is the same. It's the same thing. N's and H's are the side that's being favored in either forward or reverse. The magnitude of the K, is it large or is it small, indicating what side of the equilibrium is being favored. And by being favored, I simply mean what do we have more of in molarity units if it's concentrations, or what do we have more of in pressure units if we're looking at atmospheres for gases. So one thing we've learned so far, reverse the direction, you reciprocal the K's. Sometimes when using Hess's law, we distribute a number through the coefficients. We sometimes have to double, triple, sometimes we half an equation. If we multiply the equation by a constant, okay, and in my own words I said that means to distribute a number through the coefficients. Let's let n stand for the number we're distributing through a coefficient. If n is distributed, we change the equilibrium constant in the following way. This equilibrium constant is products over reactants, where look at those powers, they were coefficients, now we'll call them orders, are also being multiplied by the coefficient. So write this with me. I'm going to back the slide up and talk you through this. In the equation that we're looking at now, the products are C and D, the reactants are A and B. The original equilibrium constant would be product C raised to the n times C times product D raised to the n times D set over reactant A raised to the n times A and reactant B raised to the n times B. We're multiplying the coefficient. Alrighty. Then, as I put this back up, we're just looking now at the reciprocal. That's what the Kc prime is denoting. And that's just the last slide. If I reverse the reaction, we get something called Kc prime. And I distribute that through, really, all I'm doing is taking the original K constant and raising it to the power with which, oh, I'm going to back up. You're probably trying to copy that. I'm sorry, I went too fast. Kc prime is written as follows. Now, verbally, I wanted you to write product over reactant for the original value. C times D set over A times B should also be on your paper. Although I didn't type it, please include both. Product C times product D set over reactant A times reactant B. The powers with which they're raised, product C raised to n times C, product D raised to n times D, set over reactants in the same fashion. And really what's on the slide now is the reciprocal, which would represent I've reversed the direction. So you can include both, but most importantly, I wanted us to see that when we distribute through by a coefficient, we take the original K constant and raise it to that power. We don't multiply it, but it becomes the power with which it's raised. Two things we've learned. Reverse the direction, K is the reciprocal. Distribute through a number, through the coefficients, you raise to the power that very number. Let's try one. How does the magnitude, to the next page, give it some thought, it reads. How does the magnitude of the equilibrium constant, Kp, for the following reaction, I see 2 units of HI in dynamic equilibrium with H2 and I2. Alrighty. It has its original Kp value. How would it change if the equilibrium is now written as 6 units of HI in dynamic equilibrium with 3 units of H2 and 3 units of I2? Compare. What have we done? The original equation, a 2 to 1 to 1. The new equation, 6 to 3 to 3. What have we distributed through those coefficients? Therefore, n equals 3. That original Kp value would now be cubed. The new equation where we had distributed a 3 through the coefficients to find its new Kp value, we cube the original. Let's take a look at this one. 2 units of NOBr is in dynamic equilibrium with 2 NOs and Br2. Notice the Kc given, 0.014. Second equation given, Br2 and Cl2 in dynamic equilibrium with 2 BrCls. Its Kc is 7.2. What if we added those two equations together? Add the equations. Draw an arrow. Put everything on the left side we call reactants together in a single equation. Put everything on the product side, on the right side of the arrow, as one equation. Sum the two equations. What do we get in terms of a Kc? Well, as you're writing your equation, simplify anything that's on the left and the right, just as we've done all year long. Anything that's the same on the left and right can be canceled out, just as in an algebra equation. The simplified equation is something we used to call our target when we did Hess's law. It looks like 2 units of NOBr plus Cl2 is in dynamic equilibrium with 2 NOs and 2 BrCls. When I sum the two equations, what canceled? Is it Br2s were the same on both sides and they canceled out? So I don't see them in the net equation. How do I calculate the new Kc for this sum of the equation? Well, I know we're not going to add them. It wouldn't be that easy. I sum the equations, but what do we do to the Kc's? We will multiply the K values. Let's practice using all three in a Hess's law situation. Hess's law, adding together equations to find a target equation. In this chapter, we use K constants for equilibrium. Thermodynamics would have us do that for enthalpy delta H. Here's an equation. It's written down for us in our note pack. HF, aqueous, in dynamic equilibrium with its ions, hydrogen ion and fluoride ion. I see a Kc value 6.8 times 10 to the negative 4. The second elementary reaction, that's oxalic acid, H2C2O4, in dynamic equilibrium with its ions. 2 acid ions, hydrogen ions, and an oxalate, C2O4 negative 2. Its Kc 3.8 times 10 to the negative 6. Now on my slide, E negative 6 fell to the bottom line, but I think it's all right on your paper. Here's the target. When I add these two equations together, I want them to create the following target. 2 moles of HF plus C2O4 negative 2 in dynamic equilibrium with 2 fluorides and the oxalic acid. How can I add those two equations together up above to create this target? Well, let's talk through some strategy before we write anything down. For no other reason than it's written first, I always look at my first reactant in my target equation. That's 2HF. Go up into the elementary reactions and just see if you can't locate where is HF. Well, I notice it's written in the first equation, and it's the only place that it's written, so that's quite helpful. Here's what I like about it. It's on the correct side of the arrow, but I only have one of them. My target has 2. So I'm just predicting, I'm just brainstorming some ideas. I bet in the first elementary reaction we have to distribute a 2. That's going to give me the correct numbers of HFs. What else do we see? Well, the second reactant in the target equation is the oxalate ion, C2O4 with a -2. Where do you see that up above? Well, I see it in the second equation, and it's the only place I see it, so that's helpful. C2O4 with a -2 charge. I like how many I have, but I notice it's on the wrong side of the arrow. I bet, just predicting, just brainstorming ideas, I bet we're going to have to flip the direction for the second equation. Let's try that. Write this with me. Let's try that strategy. Let's distribute a 2 through the first elementary reaction. Write this down. 2 units of HF in dynamic equilibrium. That's going to be my equal sign. Pretend that's a forward and a reverse arrow. In dynamic equilibrium with 2 hydrogen ions and 2 fluoride ions. When I distribute a 2 through the first elementary reaction, that original Kc is now going to be squared. 6.8 times 10 to the negative fourth squared. The next thing we did in the elementary reaction number 2, we reversed the direction. Write that down in the opposite direction. Products are now reactants. 2 hydrogen ions plus the oxalate ion is now in dynamic equilibrium with oxalic acid, H2C2O4. That original Kc was written as 3.8 times 10 to the negative 6. The new Kc for the reverse reaction is its reciprocal, 1 divided by 3.8 e negative 6. Let's add the two elementary equations together, canceling out anything that simplifies. Anything cancels? Looks like the 2 hydrogen ions cancel right out of our equation. So when I add the 2 equations, we get our target. 2 HFs plus the oxalate, C2O4 negative 2. That's all that remains on the left side of both the equations when adding them together. And on the right side, I see the 2 fluorides, 2F negatives, and the H2C2O4, oxalic acid. When we add the equations together, we multiply the Kc values. So the first elementary reaction had a Kc 6.8 times 10 to the negative fourth, now squared because we've doubled our coefficients, times the reciprocal of the original Kc from elementary reaction number 2, 1 divided by 3.8 times 10 to the negative 6. When adding 2 equations together, we multiply their Kc's. Hit this. Write down your answer. Pause the video while you do. Hit it and record your answer. Let's see if we get a common answer. When I hit it, I found 0.1217. You may certainly have rounded a little differently, no problem. Remember, no units. Kc is 0.1217. Let's try another. These get easier the more we practice. I'll read it with you. Given that at 700 Kelvin units, Kp is equal to 54 for the reaction of hydrogen gas and iodine gas combining to form hydrogen iodide gas. Let's pause and turn that into a balanced chemical equation, recording its Kp. The reactant hydrogen gas, written as H2, I should put a little g so that you know it's gaseous. I didn't type it, but you certainly should add it on. Same for iodine gas, I2, as a gaseous form. My equal sign is now how I'm typing my double arrow. In dynamic equilibrium is what we'll say for that. 2 units of Hi, and that should have a little g for a gaseous form. Kp is given as 54. All right, so that becomes our first elementary reaction. Let's read on and see what it says next. It goes on to say also Kp 1.4 times 10 to the negative 4 for a reaction of hydrogen gas and nitrogen gas coming together to form ammonia gas, making ammonia from its constituent elements. We'll turn that into a balanced equation, where molecular nitrogen and molecular hydrogen form gaseous ammonia. They all have little g's for adjectives: gaseous hydrogen, nitrogen, and ammonia. 3:1:2 stoichiometric ratio. The Kp recorded is 1.4 times 10 to the negative fourth. So there's our second elementary reaction. First one, we made Hi. Second one here, we're making ammonia. How do we turn those 2 elementary reactions into the following? So let's keep reading. It says, determine the Kp for this reaction. Follow along in your note pack. It says, gaseous ammonia reacts with iodine gas to form gaseous hydrogen iodide and nitrogen gas at 700 Kelvin units. We need a balanced equation. We need a target. Turn those words into a balanced equation. Well, the first reactant, ammonia, NH3. Second reactant is iodine. It's molecular, I2. To form is our equal sign. Hydrogen iodide, based on charge, +1 -1, so we get HI. And nitrogen gas, molecular nitrogen, N2. So the first thing we did was write a skeleton. NH3 plus I2 makes HI and N2. And then I took some time and I balanced. I balanced with the following ratio: 2 to 3 to 6 to 1. So I just took my time and I wrote out my target equation. So here's our job. The first elementary reaction, when added to the second elementary reaction, look up above, we wrote those just a moment ago, needs to create the following target. What do we do so that when we add these together, we create this target? Now you pause the video. Strategize. What do we do to create the target? Pause, work it through, and when ready, start the video again and see if we've reached a common answer. How'd you do? Let me share what I've done, see if it matches what you've done. To the first equation, I distributed a 3 through those coefficients. I notice that when I distribute a 3, I get the correct number of HI. I needed that to be a 6. In the original equation, I only had 2 units of HI. If I distribute a 3, this is what my equation becomes. I hope you wrote it down. If not, write mine with me. 3 units of H2 plus 3 units of I2 is in dynamic equilibrium with 6 moles of HI. Notice the Kp becomes cubed. So important. It's not 54 times 3. It's 54 raised to the power of 3. When I distribute through the coefficients by a number, I raise the power. So the new Kp is 54 cubed. What do I do to the next equation? Well, I think I've just reversed the direction. I noticed that ammonia had to be on the other side from the original equation, so I simply reversed it. If you haven't written it down, do so with me now. The reverse direction. 2 units of ammonia in dynamic equilibrium with 3 hydrogens and a nitrogen molecule. Since I reversed the direction, I took the reciprocal of the original Kp, 1 divided by 1.4 times 10 to the negative 4th. Now when I add the 2 equations together, simplifying what cancels out, we get our target, don't we? What canceled? Well, the 3 moles of H2 simplified. And that must be it. And here's what our equation looks like then. The first elementary reaction, we distributed a 3, so I had to cube the Kp. I reversed the order of the second equation, so I took the reciprocal of the Kp. When I add the 2 equations together, it does indeed create my target. When I add the equations, I multiply the Kp's. What'd you get when you hit 54 cubed times the reciprocal of 1.4 times 10 to the negative 4th? 54 cubed times the reciprocal of 1.4 times 10 to the negative 4th. You get a very large number. Did you as well? 1.12 times 10 to the 9th, that's a billion. Very large Kp, showing the product side being favored. We say that this equilibrium is lying to the right. Talks about the difference between homogeneous equilibria and heterogeneous equilibria. Homo and hetero. Well, we know that every example we've worked so far in our notes dealt with the The reactants and products all being in the same phase. Now what that means, they've all been gases or perhaps they've all been aqueous. If I have a reaction that's all in the same phase of matter, we call that homogeneous. Sometimes we work problems where we have different states of matter, solids, liquids, aqueous, gases, any of those other states of matter, and we'd call that hetero. So if it's homogeneous, they're all in the same phase, and we use K in terms of either concentration or pressure, depending if it's aqueous or gases can either have molarity units or they can have atmospheres for pressure. Aqueous ions can have concentration units. But typically we're just saying here that homogeneous means the same phase throughout the entire equation. But more often than not in chemistry, our reactants and products aren't necessarily all in the same phase of matter, and we look at something called a heterogeneous equilibria. It just means different. Let's say, for example, a simple dissolving process, and lead chloride probably isn't the best to use because it's insoluble. This would have to be a whole lot of stirring, maybe with some good heat. We can convince lead chloride to dissolve a little bit. Slightly soluble at best, but we get an idea here. We have a solid ionic compound, PbCl2, when placed into water. Now maybe perhaps on top of the arrow I should have typed in water to let you know I'm just simply dissolving. It's a physical process where a salt is being placed into water to create aqueous ions. On the left side, notice it's solid. On the right side, they're aqueous ions. It's a physical process of dissolving. But this would be an example of a heterogeneous equilibria. They're not all in the same phase. I have solids and I have aqueous ions. How do we go about expressing the concentration of a solid? It might actually make no sense to say, how concentrated is lead chloride solid? It's not going to exhibit a pressure. Only gases exhibit pressure, so that doesn't make sense. And if it's a pure solid, it's not having a concentration. It's like asking you how concentrated or how dilute is water. Well, water's the solvent. It would make no sense to talk about concentrated water. So here's what we're saying. Since it makes no sense for pure solids or pure liquids to have a molarity, we do not write about them in equilibrium expressions. We leave them out. How do we express the concentration of a solid? We don't. We can't. It makes no sense. You leave them out. Look at that original equation we wrote for the dissolving of lead 2 chloride, PbCl2. Its Kc, concentration, notice the bracket standing for molarity, the concentration of the lead ion to the first power times the concentration of the chloride ion to the second power, products over reactant. The reactant isn't written for, it's a pure solid. So we just see a Kc where the ions are being used. Later on, it's actually a couple of chapters away, but it's the same idea I mentioned at the beginning of our journey that equilibrium is the focus of the next 3 chapters. It's huge in chemistry, this concept of equilibrium. This technically is called the KSP. We just written one, you didn't know it. KSP stands for solubility product constant for a salt. How soluble is a salt, KSP? Coming weeks away yet, but I can see the lesson here. If we have a pure solid or a pure liquid, we do not write them in an equilibrium constant expression. Leave them out. Write this down. When I'm reading an equation, I look for the aqueous and I look for the gaseous. Those are the only states of matter that get included in Kp and in Kc expressions. If you see something in solid form or in liquid form, leave them out of the equilibrium expression. We're not saying they're not part of the chemistry, but remember K's, they're just a number, and the size of the number that we calculate gives us an indication if the forward or the reverse reaction's being favored. When we calculated K's, we leave out any pure substance. If you see an adjective, a little L for liquid, a little S for solid, do not write about them in your equilibrium constant expression. Only aqueous and gases get written for. Let's emphasize with the following example, and I'll read it for you. It says to write the equilibrium constant expression for the evaporation of water in terms of partial pressures. So that's what our NotePack example said, the evaporation of water. So I reminded us, I just wrote it on the slide, evaporation is just a phase change where liquid turns to a gas. So I just denoted the physical process of liquid water being in dynamic equilibrium with gaseous water. We could call it steam. Liquid water is in dynamic equilibrium with steam. How would we write the Kp expression? Notice it said Kp, so I do not use brackets. That would be Kc for molarity. Kp talks about partial pressure. Still the same flavor, products over reactants. But that liquid water is pure liquid. We will not write about it. The only gaseous thing in this whole expression is the steam on the product side. Kp is a direct measurement of the partial pressure of gaseous water. That capital P stands for partial pressure. I write water subscripted below it. Partial pressure of gaseous water. It's the only thing to write about for that particular equation. Let's read through another. One more example in this lesson and it will be wrapped up.